Welcome back, everyone, and in this video we're going to kind of continue off where we left off before, where the last video we actually retarget our animation, which was pretty cool. We took animation from Mixamo and then we retarget it into our Vegeta character. So the next thing we're going to do is we're going to learn how to take that animation and export it back out, because we don't want to retarget the animation. We don't actually want to retarget it in real time like we did in the last video. We would like to actually retarget it frame at a time, and so we don't have to interpolate. So we retarget it differently, frame by frame, and then we export it back out as a GTL file. So for this lesson, we're going to quickly go through a GLTF exporter that I put together exactly just for this specific lesson and for to moving forward. So for a year now we've had an importer, now we have an exporter. And this exporter is going to be very bare bones. The main purpose of this is to just save animations out. So this way, the only thing we need to save is the armature of the animation and all the local space information for each bone for each frame. And yeah, that's pretty much it. So we're going to export the information, and on top of that, we're going to generate the binary file, and we're going to and the JSON file, and we're going to actually to download it from the web page. So the web page generates everything on the client side, and then we can actually click on a download button, and that would actually give us a file to download. So there'd be no backend server, no nothing to actually generate the file. Everything's done completely in the web page, which is really cool how I managed to implement this. So this is where you can, the idea is that we can start building tools that can do things. Like there's thinking someday in the future, if I have enough pieces built, I can build a Mixamo alternative. And this is one of the abilities. So this way, the idea is that I don't need a back-end server. I just load all the files I need, and everything would run on the client side. So let's get started. Let's start looking at some code. All right then. So I'm going to start doing things a little bit differently, hopefully, just keep it going. That maybe at the top of every lesson file, I actually start writing a process. The idea of everything that we need to do to accomplish the goal that we want. And on top of that, it'll actually make it like notes for me. So if I need to remember how to do certain things, this helps. And lately I've been seeing that YouTube has been banning people. And there's been people who just didn't do anything wrong, and they got banned, and their entire channels were wiped, and they're having a hard time getting their channels back. So I was thinking, if by some chance I get banned for some stupid reason from YouTube, these process notes would probably be beneficial if the videos are ever offline and not available anymore, because I really don't save all these videos. So once they're gone, that's it. So moving forward, I'm probably going to really spend more time documenting and the process and a lot of the steps in the code, just so that in case the videos are ever gone, at least the GitHub will be sufficient enough. I just feel bad. I'm starting at episode 133. I should have done this like episode 1. All right. So again, like I said, at the top of every page from now on, hopefully I'll have like a process or something, or like a notes area that gives you the idea of everything we need to do, and a lot more comments in the code than normal. So yeah, maybe let's just step through. I'll probably just bounce out every once in a while. So what are the couple of things we need to do? First thing we need to do is retarget the animation. So we kind of redid the retargeting before, so I don't need to really step through the idea of animation retargeting. If you're new to this, go look at the previous video, and that spent like 40 minutes talking about how to retarget animation at the bone level, bone by bone. So the first thing we need to do is we need to load in our animation file, and we need to load in our model. And as you can see, I'm using Vegeta.gtlf now instead of the Vegeta.txt file, because I'm actually going to move away from using a custom format. I'm actually going to go back to using GTLF, so now that I can export GTLF files. And I'm going to extend GTLF. So that might be a future video where I'm actually going to start extending it. This exporter, I already have some extensions built into it, but I'm not loading in those extensions yet. So I just need to fix up the importer to to do. So I think that might be the best approach in the long run. Keep GTLF, make sure it still works for like loading into Blender and everything else, into other tools, but let's extend GTLF, because GTLF doesn't allow us to save all the information that we need. So we can, and it's just, if we use the JSON version of it, like JSON and the binary, we can extend it and use it in the way we want, as long as we don't break the spec. As long as we respect the spec, but then just append to it, everything should be hunky-dory. And it does, because I do import and export with this new version. So that's going to be in the future. We're gonna really extend it, but in this video you'll see some of the extension right now. So we're going to build our source, and our source right here is very simple. So we're just going to build our preview skin animation, our preview, so we can see the skeleton. We're going to set up a human rig for it. So this way there's a commonality between one armature to another. And the rig really just stores like our bind pose, our T-pose, and our and the pose that we're going to animate. And then we just grab the animation from our GTL file that came from Mixamo. And this is our target. Look, the same setup. You know, we grab the file, we load it up, we make there's a new called skin.bind instead of skin. Right now there was like a bug, and I realized that I need to load both using the same type of bind pose. The bind pose are slightly different. There's the bind pose that I get that comes from the nodes in the GLTF, and sometimes it's kind of hard to get the bind pose in GTLF from nodes, because sometimes things aren't, most often that's not exported correctly. You have to go through these weird steps in Blender to export the bind pose into the node objects. But the bind pose is actually stored as matrices, inverted matrices, like inverted world space matrices. So I fixed up the importer to take these this bind pose that's in a specific set of data, and convert it back into local space transforms. Then I can then use it again with our regular system, where we can then do dual quaternion animations. So that's all. That's kind of, I think that was in the previous video. I'm not sure, but I probably didn't explain it. So, but in this video, instead of using the nodes to get the bind pose, I'm actually going to use the bind pose that's in matrix format. That's an inverted world space matrix. So, using that together, I get everything coded just right. All the math is right. It does work as long as I use the nodes, but the animation, like I said, doesn't have the nodes correctly. So it doesn't get exported correctly sometimes. It's just because Blender sometimes always tries to export the nodes using the first frame of the animation, and I always try to make sure that it's the T-pose, not the first frame. And I don't know why the Blender export does that. It's a pain in the ass, but in the grand thing, I'm actually going against the spec, because the bind pose is stored as inverted matrices. So just keep in mind that moving forward, I'm going to try to stay with the spec and just pull it out of that and just have to convert it. I might actually extend it where I don't need to do that, because to me it's a waste of time, and I'd rather store it in a different way. So I might extend it where the skeleton is stored in a different way, or at least the bind pose, or actually maybe, if anything, I'll create a pose section in GTLF. I'm probably going too crazy with this. So in the future, like I said, we're going to. If you have any ideas of extending GTLF and saving data, go ahead and comment, and I'll probably make a video about extending it and adding features to it that we can then import, so we don't have to waste time processing it, because that's the biggest thing. I feel like GTLF requires me to process a lot of things, and it doesn't have all the information that we need. Like, it doesn't have the length of bones, and that's important for IK. We need to know the length of bones for IK, and for some reason that information doesn't exist anywhere. All right, so we got Vegeta, blah, blah, blah. We're setting up his bind pose, which would be great if we didn't have to set up his bind pose. It would be great if we can only set it up once and load up his bind pose, or load up his T-pose. Again, that's, like I said, kind of why I want to start extending things. So we got his T-pose, and we're just going to move him to the side. So this way we can see our animation and everything else. So what else? So that's that. So I created a new object called Retarget Session. So Retarget Session is just so we can set up, so we can say here's our source rig, here's our target rig, here's our animation, build me a new animation. So this way, the idea is we're going to take one animation object and then create a new animation object, but that's more in tune to the bone structure of our target, and then save all our retarget information into that new animation object. And then we could just animate based on that object. And then we run the export test. And the export test is takes that information, exports it back out as a JSON file and as a bin file, and then it uses the import to re-import it, and then make a third object on the screen that actually runs the animation from the exported data. So this way I can see, so this way the idea is that we're going to see the animation that's from the source, we're going to see the retarget animation that's created, and then we're going to see the retarget animation that's been exported out as GTL files have been imported back in, just to see if the data is even correct. Like if the data was bad, then the animation won't work or be conky. Like, you know, I saw bugs where the data wasn't correct and the mesh would just be destroyed. You know, as long as the information's all there and correct and intact, the animation just will flow just fine. You know. All right, so let's quickly look at the retarget session. So we need to how to retarget our animation. Like I said, I'm not going to step to that too much. We got the animator, which I don't need to go through. So the retarget session, like I said, we have our target rig, our source rig, our target rig, our source animation, our target animation, our animator. So this way we can just step through all the animation frame by frame, and a way to map the bones from the source bone to the target bone. So we just need a quick mapping. So when we set our rigs, very simple, we call a function called auto bone map, which is not really a real auto bone mapping. It's just interesting because the Vegeta was skinned using Mixamo. Someone uploaded Vegeta and used Mixamo to actually skin it, so the skeleton actually has the exact same names as the animation. So this way, I just go through the source animation and see and look to see if the target animation has the exact source armature. As I look through the source armature and see if the target armature has the exact same bone with the exact same name, and if they do, I link it up. And I just link it up by saving the index of one array from the index of the other, because bones exist as an array of bones. That's all it is, and each bone array is index is very, very important. We can quickly look at that. Like I said, so I just that's how I link everything up. Look through the target rig, find the common name from the source rig. So rig target, blah blah blah. Only save map data. So I kind of just So let's see. I create a map based on the source rig. Then I try to find the commonality from the target rig. Then I go through it one more time and delete any mappings from the source rig that has no target link. So this way, basically, I make a list of bones, check to see if the list of bones exist in the armature, and then I go back to that list and say if anything is not attached, like if there's no mappings, just delete that element, because if it's not mapped, I can't retarget it. So that's the auto targeting from one Mixamo armature to another. Just in case the bones are different, that's why I did it. But like, so this way I just quickly do it. And then besides, it might be kind of the same process in the future. How to really auto map the bones. You know, search to see if they have sim names with the left and right, blah blah blah. It's kind of complicated. This is a quick function. Well, who cares? So what's the next thing? Oh, this is probably important. Yes, how to build the animation object. So we have, like I said, that's one of the important things. We need to build the animation object. So when we set our animation, our source animation, we got to build an animation object that is the same. That's that will hold the same amount of information. That will have the same time arrays. It would have the same amount of frames, but it would have its own array of channels, which is each channel is a bone animation of a specific type. So you can have like the hip rotation, that's one channel, and you have the hip position, which is another channel. So each channel is a single bit of data for one specific bone. So a bone can actually have up to 3 channels if you're going to animate its position, its rotation, and its scale. In this case, we're only going to save position and rotation, but only the hip bone is going to save its position, and every other bone is going to save rotation, because we don't really care about the position. So the original GTL file actually has the channels for everything. Every bone has the position, its scale, and its rotation. We're going to export out only the rotation and only the position for the hip. The only position we're saving is the hip. Everything else is just a bunch of repeats. Most animations don't change scale, so there's no reason to store scale at all. And most often, there's very, very few animations that actually change position. There are animations that could change position, but that's very specific to a specific model. Like, let's say there's like let's say like the skeletons from Breath of the Wild. Their bones fall apart. You know, the skeleton, the skeleton goblins and whatnot, boblins, whatever they're called, boblins. When they die or when you hit them, they fall apart. At that point, position is very important in that specific type of animation, because at that point you're changing the actual position, the initial position of the bone in relation to its parent. But like I said, most, like probably 90% or 99% of the animations don't actually change position, because we're dealing with regular animations, walk and running, and like you're not going to dislocate a person's shoulder or dislocate a person's hand from the body. So that's really what you do when you're moving the position. You're dislocating something. But the hip position changes because your body is moving up and down when you're walking or running or whatever. So the position of the hip can change in animation, and most often it does. That's the only position that does change most often in all animation. So that's the reason why we're storing that. So the animation is going to be very, very streamlined. It's very, very simple. So that means that our export data is going to have the bare essentials to actually reproduce the animation. And this means we actually store less data compared to what we get from exporting from Blender. So when we're retargeting, we're actually stripping out all the garbage that we really don't need, and that results in a smaller load and everything else, which is great. So that's really one of the big cool things about doing it this way, by customizing our exporter, because we can just trim all the fat out and make it nice and simple. So this way we have less data to download into our page, less data to load up, and to kind of build everything up, because when I do load from a GTL, I got to go through and filter everything out, because I really don't need all that information. At this point, we don't need to go filtering. We just load right up. All right, so we're going to build our target animation. So let's see. Make some references. So we have our source tracks and our source bind, because we need the bind pose of our source rig. Don't remember why. Well, I guess we'll find out when I look at the code again. I haven't touched this code in like a few weeks. I prototype everything, and then I write videos like weeks later. Good thing I got a lot of comments. So one of the first things we're going to do is the time array of the animation is going to be the exact. So like I said, the time arrays, and I think I mentioned in previous videos, is just an array of time for every frame. So every frame has an array of time. In GTLF, you can have more than one time array. So you can actually have certain parts of the bones animating at a different time rate than everything else. In this animation, there's two time arrays. One time array that actually applies to every single bone except the thumb bone. And then there is one time array that's just a single frame that has the position of the thumb. So what basically this animation says is that every bone animates except for the thumb. There's only one frame worth of information. So once the thumb is in position, it stays the same for the entire animation. So, but I want to keep that, because that's important, because if the thumb is in a certain position, we need that array. So what we're going to do is we're going to clone that time array. Now, here's the reason why I have a function for cloning instead of just copying, because originally I saved the reference, but when we want to convert everything into binary, the time array from here comes from our bin file that we downloaded. The bin file is an array buffer. And so every time you make a float 32 array, you're actually not copying so like I say, I have that time array, which is a float 32 array. It's attached to that binary file that we downloaded. So when I created that array, or when I get that array from the file, it's not a copy of the data. It's actually a slice reference to the data. So that means that array points to the original array buffer that I downloaded. Now, when I want to export it out as binary, that slice doesn't work because I need to access the buffer of that type array, and I just want and to do it I export, because I need to export the buffer as binary, but that buffer is actually the entire binary. So that's one of the first big glitches. By just exporting that time array into binary, I was exporting the entire bin file because it was attached to it. Because it's, like I said, it's just a slice. So when I say, okay, save this buffer as a binary, it actually, like I said, it's attached. It's just a slice. It's not a copy. It's a reference to a piece of a giant byte array. So I have a function called clone float 32. I actually create a brand new float 32 array and give it a size. So this means that the float 32 creates its own array buffer, so its own byte array, and then I automatically just copy the data over. So this way, it's its own copy of the data with its own array buffer. So this way, when I export it back out as a binary array, it's only that specific data and not the entire file that I downloaded. So that's the one thing I realized when I had to do this in JavaScript, is that float 30. I kind of knew, but the error like showed up in your face. It's like, boom, the buffer of a type array is still attached, and if you try to use that as an export, it's going to screw you up. So you have to. So anytime you need to, like, if you want to convert like a float 32 array, a uint 8 array, or whatever, any type array in JavaScript, you have to keep in mind, where did that come from? Did you create it yourself, or did it come from a file that you downloaded, a binary file that you loaded in? If it came from a binary file you loaded, you have to be careful. You have to clone the data if you're going to use it for exporting. So that's the big reason why I did that. And I think I actually wrote the comment here. I need to clone the data because it's an array buffer, else saving won't correct because the array might be bound to a bin file. Blah blah blah. My comment was a lot better and less verbose than what I just did. I'm sorry, but hopefully you understand what I'm talking about. So next thing we're going to do is we're going to create all the tracks, which is all the channels. At some point I have to rewrite all this and try to come up with a commonality, a common name, because I think in GTLF they're called channels and samples, and in this I just call it tracks. So I just tell animation, create a track. I give it the track. I just basically copy the track information from the source. Give it the time index that they were using, the index, the bone index that this track belongs to, because a track or a channel in GTF can have a joint index or no joint index. It's either reference to a bone or it's not reference to a bone. So this we're doing, and we have to save what type of interpolation mode, because there's several interpolation modes. And then I create a float 32 array, brand new, with its own array buffer. So because when I export it, it's just that data. It's not tied to anything. And besides, I need to create the data anyway. So it's the length of so the same length fits, because if it's a quaternion, and there's like 50 frames, it's 4 times 50. So that's how big the array is. So overall, all the buffer space is about the same size from one animation to the other. It's just the data we store in it that's going to be different, and that's really the gist of it. Let's see what else we got here. I probably wasted too much time on this. All right. So now that we have the animation target, like our animation object has our time array and it has all the buffers for every single track or channel, whatever. And next thing we do is we actually run it. So what we're going to do is we're going to run through every frame. So here we have the animator, and we're going to say function keyframe instead of I forgot there's another function that says like next, which then actually interpolates from one frame to the other. The keyframe function, all it does is goes to frame 1, frame 2, frame 3. No interpolation. We're not interpolating our animation. We're just going from frame to frame to frame. In this case, there's like, I think 32 frames, and each frame is baked in. So it's like 30 frames per second. So it's like the animation is like 1.1 seconds long or something like that. So we're going to move the frame by this much. This is our animation source, and this is where we're going to store the animation. So the animation is going to be stored in that pose, in our rigs pose. We're going to take our source rigs pose, and we're going to update its world position. So this is all the world positions are updated. So this we have the world rotation and world position of every single bone in the source armature. Then we run the retarget bone. So retarget bone is the same function from the previous video. So I'll probably just change it a little bit, but overall it's the same mathematics. The math hasn't really changed at all. So I give it the source bone name, the target bone name, and I think there's a true or false boolean that says, do you save position? If the source means hip, yes, save the position. If it's not, don't save the position. So retarget bone, that function does both. So it either it just retargets rotation or does rotation plus position. So once the retarget bone actually saves everything back into our target pose object, because we did everything into our rig source object that has a pose object. Now we're going to save it into our rig target pose object. And then we have a function that says saves target frame. So basically, everything that's in our pose we save into a specific frame in our animation, and it's actually fairly simple. So we say which frame we're currently on, and you got to remember the channels are flat arrays. So let's say the channel or the track for rotation, it's a flat array. So that means every 4 floats is 1 frame. So that's why I have to calculate the rotation index. So it's frame index times 4. So with this we get the starting point for the rotation. And same thing for position. It's a vector 3. So if it's a flat array, every 3 floats equals 1 position, and each position is a single frame of information. So once we know the index of the flat array, we can then just plop our local position and our local rotation into the right spots in our flat array. Hopefully you guys understand, because I do a lot of flat arrays. So like, you know, right now our channel is like this. So we have let's say that's our float array, right? So we have let's say this is our float array for position. We know that every position is 3 floats. So this is our float array. That means we have 3 frames worth of information. So if we know we want to say frame 1, so it's frame 0. We start at frame 0. So frame 0 times 3 equals 0. So that's index 0. So this is index 0. So we fill in index 0, 1, and 2. So the next frame is frame 2. So we know we start at 0, and the next frame is 1. So 1 times 3 is 3. So if that's index 0, 1, 2, what, 0, 1, no, 0, yeah, 1, 2, the next one is 3. So that's the starting point of frame 1. And if it's frame 2, 2 times 3 is 6, and 6 will be right here. That'd be the 6. So this way you just fill it in. So just like right here. So if I say it's 6, so 6 plus 1, which is 7, and plus 8. So this so we're filling in a flat array with information. Like I said, each element each element that we, or no, actually probably each component. Probably considered each component. I don't know. There's so many words. It's like, how do you figure out what to use? But yeah, like I said, every position or every rotation is a single frame, and this is how we're loading in the flat array. And why am I using a flat array? I know a lot of people are very object oriented. I just recently had a meeting with my boss. I think it was this week or last week, and he had a hard time understanding certain things I was doing because he's very object oriented, programming wise, and everything I was discussing was very data oriented. So data first, not objects first. So this is a very data oriented way, because everything is just data first, and then we deal with everything kind of later on. Everything that surrounds data. We're not writing code that does things. We're creating data, and then we're writing functions that manipulate the data. I think that's kind of like how I interpret it, like data oriented as opposed to object oriented. So if you have a problem understanding this, I'm sorry. And it's something that took me like 2 years to really like teach myself, because I think game development, especially if you're going to do a low-level game development, you have to be very data-oriented as opposed to being object-oriented. So like I said, all the data is flat, so you have to keep in your head how the data is divided, how the data is cut up into pieces. Even though it's one big blob of information, how is that information subdivided in a certain way that it makes actually perfect sense. So hopefully you understand that's how it is. And the reason why I do it this way is because the data already exists like this in GTLF to begin with, and without converting it in. And it's actually easy to just load the information in and just write functions that understands that information. Just use that understand that flat array, as opposed to converting everything into a bunch of objects that contains this information. And then you're kind of stuck with this collection of objects that stores data. And then if you want to export it out, you got to turn all these objects of information back into a flat array to save back into your binary file. So in essence, if you want to save yourself a lot of hassle of loading and like importing and exporting, if you just keep the data nice and flat and just build your objects or your functionality around the data, it becomes a lot super simple. Like I said, the data exists like this in GTLF. So I load it in and I keep it like that and I animate it. Now I'm recreating that by just recreating those flat arrays and then filling them in again with the new data. They're nice flat arrays. I can just save them right back out into GTLF binary. Done deal. I don't have to do any other thing, because like I said, it's already very data oriented. It's in that flat space. So yeah. So hopefully you understand. You get it. Like I said, this week I've experienced people just not having trouble understanding me because they're not used to dealing with data at this low level, at very, very low level, which is boatloads of bytes. People are very kind of surprised that I deal with bytes a lot. I don't deal with it too much work-wise, but because I don't do a lot of like low-level 3D animations type of things. But yeah, so we're not probably spending way too much time on this. This is like 34 minutes long. All right, let's get this over with. So retargeting animation, don't need to worry about. That's the last video. So when we're done, we're done. We just save all the animation back in. That's really the gist of it. So we're done. It's all loaded in. So now we have an animation. We have an animation object that has a bunch of flat arrays that represents every frame of rotation and position for our bones. The next thing I totally forgot to load in is we have to have the GTLF Explorer. And GTLF Explorer exists in Fungi Miscellaneous. BK. Crap. Or is it KB? There we go. Hope I didn't accidentally do something. All right. So let's see. So what do we need to do to export a GTLF file? If you guys are running long enough in this series, you'll probably know that I created the GTLF importer like probably over a year ago. But now I'm finally doing an exporter. What do we? So there's a couple of bits of information that we need to store. First, we need to like I said, we're storing animation or animation information. That's all we want to do is save animation information. So the first thing is all our animation information is tied to an armature. So the first thing we need to do is we need to save the skin, and the skin basically has this structure. It's just the name of the of our skin, the index in the binary, because in the binary file in GTLF is just a huge blob. It's just a big flat byte array, but all the byte array, the data is subdivided by index. So this one tells me that use accessor 5. The accessors in GTLF tell you the exact index and length to traverse that huge byte array to get that information. So the inverse bind matrix, like I said, I'm now using that instead of using the nodes, tells me look at accessor with index 5. And accessor with index 5 tells me, okay, the index, this information starts at index, index 25, and has the length of like 50 bytes. So at 25 and then count 50 bytes from there on, and that would be my slice of information from that giant array that represents my my inverse bind matrix. And the next part of the skin object is joints, and then, like I said, the joints are just an array. It's in this case, in GTLF, it stores the index of nodes, and nodes are just collection of transform information for the most part. A node could represent a bone, it could represent a mesh, can represent a lot of things. It's, like I said, to me, nodes are just transforms. It just stores the position, its rotation, its scale, and kind of like its parent orientation, like it's where it exists in a hierarchy. So nodes are just hierarchy of information. Like it's the same thing as our nodes transform hierarchy that we have in our ESS framework. And this part is my extension. I added an extension where I have an array of joints, which just points to node index. I want to add a new array called bones that automatically saves the index to the parent. So this way I don't have to go through the node system to find out where the parent is. I already know where the parent is in reference to the array. The length of the bone, so I just don't have to calculate the length of the bone, and then the level. The level is not that important anymore that it was, but I kind of still want to save it because if I feel like it can be still useful in the future. And the level is what level are you in the hierarchy. So if you're at the root, you're at level 1. If you're like the first child of the root, you're a level. If you're the root, you're a level 0. And if you're the first child or the children of the root, you're a level 1. If you're the child of those children, you're like a level 2. So it's a hierarchy. It's like how deep are you in the hierarchy tree, and that's what level means. So I want to save that's the extra bit of information. Like these two are probably the most important. If I want to keep all the data nice and flat, the parent index and the length is important because, like I said, I don't have to recalculate the length, and I automatically know what the parent is for every bone. And it's usually very important to know the parent because every time I need to do like transformation from world space to local space, I need to go check the parent's world space so I can do an inverse of that transform, so I can then convert my bones world space into local space. So that's why it's important to know the parent. For me, when it comes to doing a lot of IK and everything, knowing the child is less important than knowing the parent. The parent is more important than knowing the child. because you always have to go up the tree than you really need to go down the tree. The only time you need to go down the tree is when you want to calculate the entire world space tree. But yeah, that's it. But in the end, it doesn't really matter because the bones in the joints are already kind of sorted from parent to child. So you can actually loop through the joints from 0 to infinity, whatever length of the bones, and you can calculate the world space in that order, because in that array the parent will always show up before the child in that array. That's just how it is when you export it. Like, I don't know if it's just Blender that does it, or it's meant to be that way. No matter where tool you use to export. So far, every time I do this, it's true. So I write everything believing it's true, that in that array, every parent exists before the child in the array. So this way, it's very easy to process, and it can just process it right through. And you, as long as you have a reference back to the parent, you can then do other bits of calculation at that point. Like I said, because everything is already in order from parent to child, you don't need to know the children when you're doing a lot of these calculations. You just calculate it straight through. All right, so that's one of the first things we need. We need to add our skin. And then we need to add all our joints information. And every time we add a joint, it saves our transformation. It basically creates a node, and it saves our transformation into the node. And then I kind of save this extra information, and this is the information that we do need. And I kind of actually always reference this, like extra fungi information. So you can note that this is not part of the spec. Everything else is part of the spec. And there you go. And then I generate the inverse bind pose, and this is the function. Like, I don't really want to step through this, but this is like it's like I said, it's not that complicated. And like I said, you just loop through the array. Like I said, since it's array parent first, child second type of order by default, it's very easy to kind of just loop through and just create the world space transformation. And I convert everything into matrices, and then I have to invert the matrices, and then that's what gets saved into the flat buffer, and that flat buffer gets thrown into an accessor. Like I said, the accessor is, this one says, like, there's two things in the GTF. There's an accessor and there's a buffer. But I treat them as both as one, because most often if I'm passing in data, it's a buffer, and then I need the accessor to reference that buffer. So that slice of the array, because like right now I'm building, at this point you're building a bunch of slices. Then at the very end, when you export it, it actually merges all the slices into one giant array. And these accessors saves the index starting points and the lengths of every point. That's, like I said, that's what the accessor is all about. And that's how. And this is all the stuff you need to save the skin. So you create a skin object, you add the joints, and the joints create nodes that store the transforms, and then you create the inverse bind. Done deal. And then the next step is you need to save the animation. And this is the animation structure of for GTLF. So every time you create an animation, the animation has a name, and the actual data is samplers. So samplers, like the input, is actually an index to the accessor to which time array that this track of information is using. Output is actually the transform data, so it's either position, rotation, or scale. And then and the interpolation tells you how to interpolate the animation. And most often it's always going to be linear, and sometimes you have step. And there's other ones, but I don't know if I saved the list here. Did I save the list here? I know I had to say it. The list says somewhere. There's cubic, linear, step, and probably one or two other ones. So that's what the sampler is. So it's the time array and then the actual data array. And then the channel basically gives you the index to the sampler array, and then has a target object structure, and it tells you which node it belongs to. And path is either translation, rotation, or scale. It's literally these words. It's basically what type of information it is. Even though it says path, it's type. But the reason why it says path is because these are the attribute values of node. So it basically tells you the node, and it tells you what information to change for that node. So the idea is that you're going to take this animation and update the nodes. That's really how GTLF kind of lays it out, but whatever. That's not how I really do it, I think. But there you go. So this is the structure that we need to recreate. So we add animation, we recreate that structure. I think the first thing we do is we create the samples first. And then once we have the samples, then we create the channels. Because we have to save the data first, and then once we know the samples index value, then we can just use that into the channels. And then like this is the function that creates the accessors. And like I said, the accessors is just this structure. And like I said, all the code just creates that structure. It really doesn't do too much. So I'm not going to explain the code too much, but I'll just, like I said, just the structure. Let's see, the buffer view. I'm trying to remember what the buffer view. The buffer view is actually going to be 0, which is basically, the idea is that buffer view will have like the entire array. You can actually have more than one binary file attached to a GTLF. But anytime you're going to like export I'm not going to create a GTLF file that has entire scenes of information where it has like tons of arrays, has like boatloads of objects. Like GTLF is meant, it's meant for as a transfer protocol from one system to another, so this way you can kind of transfer data. But the way it's laid out is that you can technically build a tool that saves everything out as a GTLF file, as your project file. So it has all your nodes, and you can store all your data into separate binary files, and that's how you reference it. The buffer view is one binary file to look to get the data. So you can actually have tons of binary files attached to one GTLF file. But if you're building like just assets, then you only have one binary file attached to a GTLF JSON file. That's it. So unless you're building a big, huge thing with multiple binary files, your binary view will always equal 0, because you're always going to just have one binary file attached to your JSON file. Byte offset is the starting point for the data. Like I said, what's the starting index? And everything's a byte array, so it's just the index. So you have to keep in mind that a float consists of 4 bytes. So you have to, that's the only thing you need to kind of realize. If you have an array of floats, and let's say the float array has it's a float array that's a vec3 and it's just one frame of information. That means you have 3 floats. The size of that information is 3 floats, but it's 3 times 4. It's 12 bytes. So you're storing 12 bytes of information. So that's the only thing you can keep. So, and the interesting thing about the buffer is that if you, like say, this data view is probably like a float 32 array. So if it's a float 32 array, right? Inside, I can ask for its buffer. Once I have its buffer, I can just say, give me its byte length. So I don't have to actually calculate the byte length. It's easy to do. Like I say, just take the float array length times 4 or times 3. But at this point, since the array buffer is already considered a byte array anyway in itself, I can just say, give me its byte length, and it's done. So you can actually save yourself from actually calculating anything by doing it. And that's kind of one of the reasons why I said in the earlier is that I want each float array to have its own array buffer. So this when we export it out, if I say byte length, if it was still attached to the binary file that I downloaded originally, it would probably say million bytes. But in this case, I only need 12 bytes. It's really 12 bytes, but it's attached to the wrong buffer, array buffer. So by making sure you clone your float 32 arrays and into his own array buffer, everything else can be like simplified. So this way I can, and it's easy to convert a float 32 array. Like if you have a float 32 array that has its own array buffer, I can say, well, here's the array buffer and add it to a uint8 array. Now here's the thing, I'm not cloning the data. Every type array references back to an array buffer. So at this point, I'm not actually creating a new array. I'm actually creating a new reference type to that specific buffer. So the original data is a float32 array and has its own unique byte buffer. And I'm actually creating a new reference to that byte buffer. So this one, instead of reading every 4 bytes as a single float, it actually treats every single byte as a byte. And that's why I say it's kind of, so this way it's super easy to convert a float array into a byte array by keeping everything unique and in its own way. Yeah, and that's it. And we kind of save it, and then like a lot of this stuff gets compiled later on. So that's how we create our accessors and our buffers. And sometimes you like I'm trying to remember. I can't remember which one, but there is, for the animation, you need to store like the minimum and maximum of a certain value. I can't remember which one it is. I think it's the time or something, but it's a scalar. So I need to know what the minimum and a maximum value is for that specific buffer. So because when you import it, you need to know the min and maximum. And that's what this function is. But I only need for the scalar value. So this way it just loops through the array and just calculates the minimum and maximum value and returns it back. So if I need to do like a vector 3 or a vector 4, which is a quaternion, I need to create different functions to do it. But so far, I don't need to save minimum maximum. The only other time I need to save minimum maximum, which I haven't done yet, is when I want to export a mesh. And the vertex array, the vertex array need to know the minimum and maximum position of all your vertices. So this way it creates a bounding box. So by knowing the minimum and maximum of a vertex array, you can build a bounding box. So so if you want to do like a bounding box collision detection, you already have the bounding box information. You don't have to go looping through all those vertices to figure out what's the what's the bounding box. So like I said, right now I'm not exporting meshes yet. In the future I will be, and I would have to create another function that does bound vector 3. So this way I get the maximum for a vector. So now the last thing is, once we have all this information, I'm going to show you the constructor. So we save all our nodes, we have saved all our skins, or meshes, or animations. I haven't done this yet, but this is going to be something I want to add to the future, where I'm going to store VAO information. So this way I can probably skip a lot of things and just build VAOs directly from the binary file very quickly without processing the GTLF file. So that's another extension I want to add, but it's not in there yet, but I do want to do that. Yeah, so we have all this arrays information that's array saved in the right structure. So when we do an export, it's very it becomes kind of very simple. So let's look how we export the binary. So every time we create an accessor buffer, we kind of just add how many bytes we saved. So this way, let's say we have like 10 arrays of float 32 arrays, 10 of them. We add up the total bytes each one does as we're adding it, and then at the end we want to make one giant byte array, right? One massive giant byte array. So at that point we already know the total size of all of our mini arrays, and we create a new byte array. This is basically really just a byte array. Byte arrays are uint8s. So we create a brand new byte array with its own array buffer with the size, or with our total size of all our mini buffers. And then all we have to do is just set the data. So we pass in the data for each buffer view, and then the offset. So as we're calculating, or every time we add or put together our accessor, I save our byte length and I save our byte offset. And the byte offset is really the current buffer size that's in there. And then at the end, we increment the buffer size with our new byte array. So in the end, it's really easy to really just merge all our byte arrays into one giant byte array, as long as you keep track of the total size and the start of each one. Really, that's it. Like, you don't even need the length to store it. You just say, just here, just append to it. And when we output JSON, it's like very simple. You just rebuild everything by using the data that you have at hand, because all the data is already in there and stayed in the right structure. And I build it like this as text because I want it to be formatted very well, so this way it's human readable. A lot of times I can probably do a JSON stringify on the object, and it'll do a fairly good job, but then it treats everything as one big, huge, flat string. This way I'm able to I'm able to put in new lines. I'm able to put tabs, like I said. So I'm rebuilding the GTL file as something that's human readable. And I just go through each array that I showed you at the constructor and just build the structure over again. And that's all I'm doing for the GTL file. And the buffer is really just a big giant string. Yeah, and in the end, the only thing you have to keep track is what's the BufferView, which the total length, and the URI is the name of the binary file. Like I said BufferView equals 0. This is where the BufferView exists, inside buffers. Actually, no. Buffers is buffers. BufferViews is what I think accessors are. Which accessors are... It's tricky. It's funny how like these things, like accessors and BufferViews, are kind of intertwined. But the file that the video I created about GTL importing has a lot more details of these things. I don't really want to dive too deep into this. I just wanted to kind of show you how the exporter works. Since as long as you know the structure, you just spit out the structure back out, because all the information is pretty easy to kind of attain. So that's the GTL exporter. All right, this is ready. How long is this? Oh my God, it's almost an hour long. I am so sorry. This is kind of complicated. Export information. So this is the last piece of the video. But this is going to be our exporter. So we have a function that exports armature, exports animation, and this is how I export the armature. I just go through our armature, I add a skin, and then I go through and just create a joint for every bone. And then I tell it, hey, create me that inverse bind pose. So when I create a GTL export file, I pass that into these functions that kind of like does the actual final work. Like the GTL export object is built where you can just build each main structure and then every element for every structure that's important, like every skin element, every mesh element, every accessor, whatever. And these two functions kind of just takes that collection of functionality and it starts using them to kind of just throw information into all those arrays that exist in the constructor. So that's how we save our armature right back in. Like I said, like we kind of already stepped through all the functionality. And same thing with the animation. It's not overly complicated. Like I say, we kind of just created accessor buffers for our time arrays. And then we go through our tracks. If the track is rotation, this is the kind of information we need. If it's a position, that's the kind of information we need. And then we collect some more information, like different time indexes and node indexes, the accessor index, the sample index. So we create accessor, we create the sample, whatever, and then we finally create the channel. And that's it. And that imports everything. And then we already saw what the output JSON file does. So we kind of save everything kind of back out into these global variables. And then at the very end, we have this, which is pretty cool. So the idea is that let's say we take the JSON file and we create a blob out of it. And then we create like this like URL object. I think it kind of converts everything to like base 64 or something. And it creates a URL. And then you kind of just like this is connected to a link. So here's a link. So we have a link that says download JSON file, and on click it says download JSON, and then passes this object. So it's a reference to the link object. So I basically create this blob URL and I save it into URL. I set target to blank, so this way it's kind of like telling it to create, instead of loading the data into this current web tab, create a new web tab or create a new window. It's like it needs to be created outside of this tab, basically. And then you set its download file name, so you can just say GTL file or bin file, and as long as you set it as an oct stream, the browser won't try to load the file. It'll actually initiate download. So that's like kind of like a magic trick right here. Like when you click the link, it won't load the data. It would actually say, well, I don't know what this data is. It's an oct string. It's just bytes of array. It's just bytes of information. I don't know what to do with this bytes of information. Here, do you want to just download it? And that's how it really works. And there we go. I probably shouldn't click save. So if we go back to here and we go to here, and there you go. So that's the center is the animation that we loaded. This is the retargeted animation. So when we go from frame to frame, and we save the data out, this is what this Vegeta over here, the left Vegeta, no, yeah, left. No, that's right. I'm sorry. I don't know I have problems with my left and rights. So that's my right side. So that's the right Vegeta is the actual retargeted animation, and then left Vegeta, which has its bones and everything, is the exported data that we're testing. And right up here we have the JSON file. So all I have to do is just click boom, and there you go. Test.jf test GTLF is downloaded. Boom. Test.bin is downloaded. Done. All that data we created now is just downloaded. We're done. We actually created a tool that's completely on the client side. We retarget the animation and we save the animation back. So now what we can do is we have test bin and test GTLF. I can say, well, let's play it. And there you go. Now this file, the only thing this file does, super simple. All it does is loads the test bin and a test GTLF, loads the animation from it, which I call default. I don't give it a name. Like I didn't build it, so it's the default animation. Remember in the previous one, it's like super long. Let's see right here. So that's the name of the original animation. It's armature, mixamo, layer 0, whatever. But when I create the animation myself, I just say, well, default. So this way I don't have to worry about like figuring out the name. It's just like anything I export and save, I just say default, because I'm only saving one animation. There's no reason to name it, but I need a name, so default. And then animator. Then on animation, we just animate it, and we don't need the animation object, and that's it. Super simple. Like we don't even need this animator here. The animator needs to exist in its own file. But like I said, we load the mesh, we create a pose, create an animator, and we animate it. Done. And like I said, this is the data we exported. We retarget it and we exported it, and now we're loading it back into a test page that all it does is just reads that exported information and plays it. And there you go. And it took me like about an hour and 3 minutes to explain the entire process of basically doing a GTLF exporter for our retargeted animation and to download it. My throat's killing me right now, and I'm not going to spend time blabbering at the end of the video, so I'm probably going to say I hope you had enjoyed it. I hope you had fun. I'm sorry for a little long video. I try to keep these shorts, but sometimes these topics are very, very hard to explain. It just takes a while. So hope you like the next. Hope you enjoyed the video. The next video is going to be fun. I'm actually going to record it in the next couple of minutes. Hopefully my throat won't die on me. So the next video is we're going to take this animation that we just exported, and we're going to turn them into data textures. And the data textures are going to be used to do the entire animation on the GPU. So we won't even need the animator object at all. No animator object. We wouldn't even need the pose object. We won't need anything anymore. We would just need the mesh, a shader, and that data texture. and all the animation will just kind of run. And so that'll be the next video. So please like and subscribe. Follow me on Twitter if you want to see the progress of all these projects that I'm doing. If you enjoy the videos and they're really helpful, they're really helping you out, teaching you, go to my Patreon and just donate $1. $1's fine. You want to donate more? That's great, but $1 is great. If you, it's good enough for me. Like I said, it's a tip. Patreon is my tip jar. So if you want to give me a tip, just $1 will do. So enough self-promotion. See you guys at the next video.